Hello everybody. So today we're going to be talking about a concept that relates to trees called a minimum spanning tree. So basically, you know that sometimes we have graphs and then we have weighted graphs, which is basically graphs with its edges with edges that have weights. So let's draw one of those graphs right now. You'll see what I mean soon enough. Okay. 6, 5. And then, okay, I hope that's neat enough for you to read. Okay. It's not too easy to draw with a mouse, so bear with me. Oh, yeah, and these edges. So yeah, so these edges basically have weights, which is to say these edges themselves have value. Oops, that is supposed to be a 2, and then 3. Yeah, so one question that we deal with when we're working with graphs is that if we have a graph, can we construct a tree from the graph's nodes? Or like, so we take out certain edges, and then it by definition becomes a tree. So let's review. A tree by definition is one graph with n nodes and n-1 edges. So if we know that, then we can see if we, for example, let's just grab an eraser here. So if we erase certain so for example, now this thing becomes a tree because there are n nodes. There are 1, 2, 3. There are 6 nodes and there are 5 edges. So this makes it a tree. So this is called a spanning tree. So basically a tree that uses the nodes and edges of a graph. So then the question arises, if we have a weighted tree, how can we make a tree that has edges with the maximum total number of weights? So I hope you understand that. So if we add all the weights in the spanning tree together, how can we maximize that sum, right? So it turns out that there is an algorithm for constructing a maximum spanning tree, it's called. So first, so the first step of the algorithm is erasing all of the existing edges. So we start off with just a normal tree. Okay, just a normal tree with no edges. And then let's just keep the values there because I don't want to come back to it later. So first we create a list of all of the edges in this graph. But we're going to sort that list by weight. So I'm not gonna do all of the, actually I think I can insert text here. Ooh, okay, that's not very good. Let's just keep with the pen. And then yeah, so sorry, this one's a 4. Yeah, this is not very neat at all, but I hope you can still understand what I am trying to do. So these are all of the edges in the graph, ranked, or rather sorted based on their weights. Okay. So then what we do is we iterate back, right? We iterate through this list backwards. So we start with the edge 3, 4. So and then we assume that we are going to add this edge here, and then we are going to check all the components of the graph. If we recall, a component means all the parts that are unconnected. So this is a component. So we verify whether or not this is a valid tree. And we see that it is. Okay, and then we are going to add another edge, the second last one. Okay, and then we see that this is indeed still a valid tree. And then we go to 2, 5. So 2, 5, okay, still valid trees, no, nothing invalid. And then we go to 2, 3, okay, another edge. And then by this way, we are maximizing the final sum because we are getting the largest sum possible by going through it backwards. And then 1, 5, 1, 5, and then 3, 6. We can't connect 3, 6 anymore because that would make it an invalid tree or not a tree. And then we can't add 1, 2 either, and nor can we add 5, 6. So this is the maximum spanning tree for this particular graph. We have a tree, and then the sum is 5 plus 5 plus 6, that's 11, 20, 27. So the sum is 27. That is the maximum spanning tree for this graph, and we have constructed this tree by going through this list of edges backwards based on their weights. I hope you learned something today. Goodbye.